Welcome everybody. It is a great pleasure to welcome Adam Riess to the CosmoVerse series of seminars. Thanks a lot, Adam, for accepting our invitation. Adam requires an elaborate introduction because he's widely known for his groundbreaking contribution, including, of course, winning the Nobel Prize in Physics and numerous other prestigious awards, which I won't delve into today. So I will just say that Adam received his PhD from Harvard University and now is a professor in the Department of Physics and Astronomy at Johns Hopkins University in Baltimore. And today he will present Thanksgiving for JWST in 2023. Adam, whenever you're ready, you can start, please.
Okay, well, thank you for inviting me to give this talk. So when we talked about a date and a time frame, I realized it would be very close to the Thanksgiving holiday in the US, which is tomorrow. And this is I know this is a US holiday, but I think a harvest holiday is a common thing in many countries and cultures or whatever, a time toward late in the year when people have harvested things that they've worked through the whole year and give some sort of thanks for them, gather with people. So today is the traditional day in the US where people spend long periods of time at airports and on highways stuck in traffic so that they can give thanks. So I'm going to give thanks today for the James Webb Space Telescope because these seeds were planted about 30 years ago, a tremendous amount of work by many, many people. And I know personally, I'm very grateful. I was not one of those people, so I'm very grateful to them for spending careers building this telescope. I'll freely admit I was skeptical that it would succeed. Not so skeptical that I didn't put in a proposal, but still skeptical that it would succeed. And it really has succeeded tremendously. For our group, the SHOES team, 2023 is the first year we got data from James Webb Space Telescope. We started getting data in January, and all our data came in this year. And so we're harvesting it now. And so I'm going to give thanks and show you some of the harvests of JWST, some of which have been published before, but some of which have not. So you'll see combinations of things. Okay, so let me get started then. So I know this group really needs no introduction to this problem, but I find myself congenitally unable to not provide an introduction to the problem because, well, you never know. That's what you do in colloquia. So I'll just say that cosmology has made tremendous advances in the last 30 years. We know something about what the universe is made of. We have a model, lambda CDM. It's a good fit to much of the data, which is why it is our standard model. And yet a lot of physics in lambda CDM is still unknown to us, particularly the fundamental physics of dark matter and dark energy. And so therefore, it's incumbent upon us to test the cosmological model as best we can at all parts from end to end. And the Hubble constant provides a unique opportunity of any cosmological aspect of the model because it's one of the few things that we can predict using the model at the beginning of the universe and that we can measure locally to good precision with many techniques. And it encompasses our ability to explain the whole expansion history of the universe. So, of course, the universe starting out dark matter dominated, decelerating, then dark energy dominated, accelerating. Of course, one can use the very precise data from the cosmic microwave background, and in this case, Planck, to calibrate the model, essentially varying 6 free parameters and a number of ansatz until there's good agreement between the power spectrum, the temperature fluctuations, the polarization. And then once done, one can then use this calibration and knowledge of the model all the way to the present time and predict the value of the Hubble constant, which is 67.4 plus or minus 0.5. And then one can also directly measure distances and redshifts in the local universe following the definition of the Hubble constant, which is why we call this direct, because it doesn't involve the cosmological model, and compare those. And so I'm going to talk about work related to this latter approach I meant ladder, but also ladder approach, where you measure distances. And in our case, I'm going to talk about using sort of gold standards of distance measurements, using geometry to calibrate type 1a, Cepheid variables in nearby galaxies, and then using type 1a supernovae in those galaxies once calibrated to measure the expansion of the universe. And the work I'm going to talk about involves following on work from the SHOES project, which began, almost 20 years ago, to measure the Hubble constant with certain elements that I think were improvements over past efforts, which themselves were very successful in this endeavor, particularly canceling calibration errors using HST for the Cepheids measured in rung 1 and 2, observing Cepheids in the near infrared to reduce the effects of dust, using the best modern supernova data, lots of comprehensive analyses of variance of the analysis, error propagation, et cetera, et cetera. And the culmination of all this was last year, data release, what I would call data release 5 for us, because we've been doing this many years, this distance ladder that you see here. Okay, so I'll cut to the punchline. As many of you know, the result that you get following this local approach is in tension with what we see with Planck and Lambda CDM, at least 5 sigma, as we published it last year. There's updates that have come along the way. It may be 5.3 sigma, it may be 6 sigma. At this point, the exact number of sigma probably is not a critical issue, other than I think it's readily recognized as at that level significant. So we invested in analyses of various variants, all kinds of ideas that people have suggested, varying things in the analysis. And at the end of the day, 67 variants in 12 categories, and we struggle to come up with any answer below about 72 and a half, making this a very sticky problem for us. And not just for us, but as the community has largely recognized, if you take various approaches to calibrating the cosmological model, but at early times, sort of following a similar route as what I described with Planck, you do tend to get something 67, 68 around there. Very hard to escape that. If you measure locally, switching out different rungs of the distance ladder I described, you tend to get things in 70 to 75. So, you can't really pin this on any one particular aspect, although there's no doubt the strongest tension comes from these most significant results with smallest uncertainties, Planck and the SHOES results that I've talked about. So what is going on? For 10 years, I would say, we've speculated on both errors or new physics. Here is my sort of top 10 list going back in time of what were the most likely sources of explaining this in terms of an error in the measurements, not new physics. And we and the community have gone through these, addressing them, analyzing them, considering them, entertaining them. And at this point, I'm claiming that at least the top 9 of these have been eliminated. And I don't have time to go into them individually, but if you want to sort of brush up on or relook at the evidence for that, there's a QR link here to a spreadsheet that covers about 60 or 70 papers and sort of goes through, how they address these different ones, what they concluded, what was found, and like that. So I encourage you to take a look at that if you have questions about that. What I'm going to talk about for the rest of this talk involves number 10, which is near-infrared Cepheid crowding. And I'm going to talk about it because it was one of the concerns, but also it is something that the James Webb Space Telescope can quite uniquely address. So just remind you of what this problem is or represents. When we measure distances to galaxies that host type 1a supernovae using Cepheid variables with the Hubble Space Telescope, we see a Cepheid variable like the object you see in red. We find it from its light curve, and then we follow it up in the near infrared to reduce the effects of dust. However, that star lives with other stars, and when we see its image, it's superimposed on the scene that you see, which, as I said, includes many other stars. And so there can be some blending of the light of the Cepheid with whatever it sits on top of or what sits on top of it. And so this effect is called crowding. It normally would produce a bias in your measurement, but of course, people have recognized for a couple of decades that this was a possibility. And so the standard way to address this is by throwing down fake images of stars in the same frame at known brightness and remeasuring those stars as though you didn't know that they were what their brightness was, but you were following the same measurement path and accounting or correcting for the effect of crowding, which is just another fancy way of saying you measure the background empirically by throwing down fake stars. So that ought to work fine. However, it does produce the largest source of noise in the measurements because while you can correct for this effect statistically, so you don't bias your distance measurements, it still does produce fluctuations in the measurements of any individual object, as an individual object may have a more direct companion that it landed on, or it may be on a particularly empty region. Now, the virtue of having a telescope with far greater resolution than Hubble is all the images of stars become less blobby and blurred. They become smaller because your point spread function is small. And it so happens in the case of nearby galaxies, this becomes so pronounced that you actually get to see Cepheid sitting on essentially nothing, naked background. And so you more or less, not perfectly, but, to factor of 5 or 6, drastically reduce this effect so that it basically becomes a negligible issue and greatly reduces the noise. To put a little more detail on this, if you look at the period luminosity relationship of Cepheid variables, let's say in the Large Magellanic Cloud, you could see, first of all, how good that relationship can be, but how it looks somewhat different at different wavelengths. And so generally, we like to make our measurements further to the red to avoid the effects of patchy dust, which you can see can affect individual Cepheid measurements. But you don't want to go so far to the red, otherwise you start to lose resolution and you start to lose contrast. And of course, Cepheids are relatively hot stars. Their spectrum peaks in the yellow, so you don't want to go too far to the red. And so the sweet spot, I would say, for measuring Cepheids has been the near infrared. However, Hubble, as I just described, but now here in a little more detail, has the lower resolution. And so this crowding effect that I talked about, even if you correct for the bias, still produces the dominant source of scatter or dispersion in the measurements of Cepheid variables. So in this case, JWST is a dramatic improvement in the precision of those measurements and reduction in the noise. So with Hubble, in the visible, we had excellent resolution, but the effects of dust. In the near infrared, we had low dust, but still the large crowding. So JWST is really giving you the best of both worlds in the same set of images. So we have 2 programs with JWST, one in cycle 1 that just completed this year, and one in cycle 2 for next year, that are looking at the hosts of 15 type 1a supernovae. And we're observing in 3 filters, FO90W, which is very close to a conventional I band, F150W, which is almost the same as HST's near-infrared filter, F160W, which really makes this a very direct comparison because we're observing at the same wavelength, and then a redder filter at about 2.8 microns. So in cycle 1, we observed 6 hosts, 5 type 1a supernova hosts, and NGC 4258, which is the geometric calibrator. And we selected the galaxies that were the richest in Cepheids, had the biggest numbers of Cepheids, so we could get the best statistics. We observed all of these hosts in 2 epochs. I want to say a little bit about this. 2 epochs it could have been more than you needed, except we were very concerned about the photometric stability of JWST. So we wanted to be able to observe at different times because it was unclear yet whether the mirror configuration would be stable. We also wanted to be able to confirm the identification of the Cepheids seen with Hubble and followed up in JWST by seeing the things vary. And then we wanted to be able to rephase the Cepheids. So we know the periods of the Cepheids, but knowledge of where they are in their light curves has elapsed over the 10 years since they were first found with HST. In cycle 2, we're going to observe a different set of host ones with the largest background. And I also direct you to the CCHP has a cycle 1 program that is observing 10 of the nearest type 1a supernova hosts in some different filters than we are. Okay, so in February and May, we observed our first 2 galaxies, NGC 4258, which is the calibrator, and NGC 5584, which is one of the richest hosts of Cepheid variables, putting 1 module on the disk. Here's where the Cepheids are, and 1 module off of that. Now, as I said, we were concerned about whether JWST would be stable enough to give us good photometry, and we needn't be concerned because it turns out things went much better than anybody expected. However, we looked at the monitoring data, so there's wavefront monitoring that goes on of JWST every day or two to see if there's been any action in the positions of the mirrors, in which case, if there is, some adjustments are made to bring it back to perfect focus. And so during our observations, we were relatively lucky. There were no major focus events and corrections occurred in between. But even if there were, just to give you a sense of scale here, this is the encircled energy. So the amount of energy in the core of the point spread function. And even these fluctuations in our filters would have been at the maybe 100th of a magnitude if we were unlucky and there had been a tilting of one of the mirrors, as can happen if a micrometeor strikes one of the mirrors. And this was work done by Marshall Parent to retrieve these. Okay, so then we followed up the Cepheids. Here are the color magnitude diagrams of these 2 galaxies. The Cepheids were found exactly where they were expected to be, both in position, within about 0.3 pixels of their expected position, but also you could see in terms of color, as I said, they're yellow stars. They live in the instability strip here, so they're not like red giant stars over here or young blue stars over here. Okay, so here are the postage stamps of a small set of the individual Cepheids, so you can see how good the images are. So you could see with HST, we had very good resolution and contrast, but as I said, the effects of dust. So then you want to go to the near infrared, and this is where JWST really shines because compared to Hubble, where the resolution was relatively worse by a factor of 3 or 4, you can see the dramatic improvement in just the resolution of these images. The sensitivity, of course, is better than Hubble as well. So the combination of the two gives us truly clean images where the effects of crowding become negligible, although we still account for them. We still throw down artificial stars and do the entire procedure, which one normally does. It's just that it becomes such a very small effect. Okay, so as I described, we observed for 2 epochs each of these galaxies. And so one of the things we found that was very impressive to us is that if you look at the difference in the magnitude of the individual Cepheids between the 2 epochs, that's the y-axis, versus their log period, what you see exactly follows the simulations, which are shown in gray, of what random phase Cepheids how they would appear in this space. And so, for example, if you observe Cepheids whose period corresponds to exactly the time separation of our 2 images, which was 22 days, then you're always seeing them at the same phase, in which case the difference is 0. But if you see them in any other phase, then you're seeing a difference. And that difference you're seeing, the sign of it and size of it, directly measures the phase of the Cepheid light curve. So here's color coding the exact same diagram, except we're color coding it by the phase of the Cepheid. And so here's the Cepheid on the rising branch, colored red, on the declining branch, and kind of green and blue. And so because of the asymmetry of the light curve, they spend most of their time declining, which is why this wing of the phase diagram is most populated. This is the when the Cepheids are in decline. And so, as I said, you can use this to recover knowledge of the phase, which allows you to get closer to the mean of the Cepheid light curve than you would from random phase or even square root of 2 improvement. Okay, so moving right ahead, you measure the period luminosity relationship of the Cepheid variables in these two galaxies with JWST, and you compare that directly to what you saw or what we saw with the Hubble Space Telescope. So the points in gray are the period luminosity relations as seen with Hubble, and in red are what we see with JWST. Here are postage stamps of just a typical Cepheid variable seen with both of them. And the reduction in scatter is quite dramatic. I've never seen an improvement like this in any iteration of data I've gotten to personally work on. It's about a factor of 2.5 improvement. And so many properties go as the square of the scatter in terms of weight and things like that. And so it really is a quite dramatic improvement in quality. And yet the difference in distance between these two galaxies measured as the difference in the intercepts, and that's the key thing that we're measuring to measure the Hubble constant. It's really the difference between rung 1 and 2. That's the only job Cepheids do. It's very consistent between what was measured with Hubble, shown here in gray, and what is measured with JWST. And I want to emphasize the photometry here in this case was all done by Gagandeep Anand at Space Telescope Science Institute using Dolphote, which has become the de facto package for measuring point spread function photometry with JWST. And this is the JWST edition of that as curated most recently by the ERS group. And so this is, I would just say, standard. Anybody could grab this data reduction package, run it on these images, and this is what you would get. So there's nothing kind of fancy or complex going on. Okay, so let me talk a little bit about the distance measurement then to this galaxy. So what you see here are various distance measurements made to this galaxy versus what you would have expected for, I'll say, Planck calibrating lambda CDM, i.e. H naught of 67.5, and that's shown here in green. And of course, this big chasm you see between them is what we call the Hubble tension. So these are our past measurements of the distance with Hubble. And there's some unique aspects, quite unique aspects of this particular galaxy and this particular Type 1a supernova in it that I want to talk a little bit about. Now, the results on the Hubble constant from the SHOES team are based on 42 Type 1a supernovae. So you might think, okay, I really need to look at the whole set of 42 before I get any results that I can look at. However, this one object provides the strongest test of any of the individual 42. Why is that? Well, it's because it has the best leverage individually. Why does it have the best leverage? Well, it has the highest combination of distance and size of its Cepheid sample. Its supernova, 2007 AF, has the most independent Type 1a supernova light curve. So unlike most Type 1a supernovae, which are observed by maybe one survey or two surveys, this supernova happened to have been observed by all four of the major surveys, CSP, CFA, SWIFT, and K, and they all agree on the supernova light curve. It's a prototypical normal Type 1a supernova. Its color is, in the parlance of fitting, 0, which means it's neither red nor blue. It has a normal light curve shape. And yet, this one object has more tension individually as one object than any other in the set of 42. It's about 0.4 magnitudes, more than 3 sigma, all by itself from Planck and lambda CDM. Now, I'm emphasizing this so much because this is the reason we chose to do this object and do it first, is because if any set of measurements would have revealed a systematic error, you would have bet on this one, because by having the biggest tension, some unknown systematic error should be strongest in it because it was showing the most tension. It was, in some ways, the furthest for its significance from Planck. And it had the largest data set, as I said, the most supernova observations. So this was really the best chance. And yet we don't see it. These are various combinations of using the JWST filtered data that looks very consistent. And I also want to draw attention to, this is one object where an independent group, the Arakaria project, went back to the Hubble archive and grabbed the pixels themselves and redid all of the measurements from scratch with no overlap of anything the SHUS team did, and got much the same answer. So it's fascinating in that sense. If you want to ever look at just one object to understand the Hubble tension, this would be the one to do. I even looked a little bit further, and this object lives in the Virgo 3 cluster of galaxies, just an extension of Virgo. It has about 75 galaxies in it. And the distance you get from the Cepheids and any other measure that I've seen are around the low 20 megaparsecs. It would have to be out to like 30 megaparsecs to match the Planck value, which I haven't seen any literature values claiming that Virgo is out that far, but the full range is much smaller than that. So let me move on to what else you get from this data set from JWST. With the same data, you can observe tip of the red giant branch by looking at these regions out in the halos. This is NGC 4258. And I'm going to talk a little bit about work done by Gaggandeep to measure tip of the red giant branch in NGC 4258 with the JWST data. So this is work Deep has done. He's done the edge detection. You can see pretty clearly the tip of the red giant branch in this case. And he, from his analysis, finds a full range of results ranging over about just 0.02 magnitude. So it's a pretty well-defined tip in this case. I don't normally measure tip of the red giant branch, but my comments are that I can see it, which is a good sign because sometimes the tip of the red giant branch can be very fuzzy and you don't really see it. And I'm going to show you a case of that. But this is a case where you could see it pretty directly. So let me move on to another galaxy. Let me move back to NGC 5584. This one has had kind of, I will say, a controversial measurement of its tip of the red giant branch in the past. So in the CCHP sample from Friedman et al. And Zhang and Li et al., they give a distance of 31.82 plus or minus 0.1. That doesn't sound very controversial. It's exactly the same distance that you get from Cepheids. However, it was not measured in the halo. It was measured in the outskirts of the disk because it was using the data from the Cepheid program. So it was just measured in these little hatched areas that you see here, just covering 1 square arc minute. And this is the color magnitude diagram. So here's a case where you can't really see the tip to your eye. And in fact, this was reanalyzed by the EDD team, Anand et al., using their own photometry. The photometry was not available from this measurement, so Deep and others measured it themselves, and they don't see any evidence of the tip in this case. So they call this one undetected. And the CATS team, Skolnick et al., also tried to analyze this one and concluded that the contrast ratio, the ratio indicating the number of stars above and below the tip, was less than 1 for any distance. And so they concluded that any detection of the TRGB would have been insignificant in this galaxy. And this is one of 4 type 1a supernova hosts that are in this category of, I'll say realistically, probably being too far for the Hubble Space Telescope to have observed. Now, what about with JWST? So this is work that Deep did in the same way that he did for 4258. But in this case, we're actually measuring out in the halo module that you see here. And so according to Deep's measurements, the tip is clearly visible, and I can see it as well. This is the edge detection that you see. And according to Deep, if you do the same edge detection methodology as he did for NGC 4258, and you calibrate this with NGC 4258, you get the same distance at 31.80 that we get with Cepheids that was previously claimed for this tip of the red giant branch. And so I jokingly say, surely this will end all discussion on this, but I'm sure that there is more to come. But at this point, I would say that there is a good measurement of the tip of the red giant branch distance to this galaxy with JWST, and it agrees very well with other measures. Now, there's even a third measure that can be used, and this is a new standard candle called JAGB. And JAGB is a clustering of carbon-rich AGB stars that live in a fairly narrow range of mass for reasons related to what allow them to appear as carbon-rich stars. And I direct you to a nice recent paper by Abigail Lee, 2023. But basically, it's a clustering of stars, and these were enhanced in their visuals, so you can see them here in this box that you see here. And we see this in the JWST data in NGC 4258, and we also see it in NGC 5584. And so the method is to make a luminosity function of these stars and measure a moment of the luminosity function, the mode or the mean or the median or something like that, and that this is your standard candle. Now, this is work done by Sean Lee. The results that you get are broadly consistent with the tip of the red giant branch distance, the Cepheid distance to this galaxy, and not at all with the Planck results. However, I will say, I think it's early days for this method. And in particular, we find that the breadth of this feature, as well as the clear contamination from other populations of stars that exhibit the same, that live in the same region of the color magnitude diagram, give you a kind of non-uniform luminosity function. Here you can see it's quite asymmetric. Here it's much more symmetric. And this results in the sensitivity of the results of what a distance would be to the choices that you make. And so we tried various choices that are made in the literature, using the mean, sigma clipped mean, using the median, using a mode, smoothing that mode by various amounts. And the result that you get can fluctuate at a couple tenths of a magnitude level. As I said, it's broadly consistent with the Cepheid and TRGB distance, but I would like to see more ways of standardizing this method so that it isn't as sensitive to the choices. So I think that's work still to occur. Okay, so let's go back to the harvesting mode. So these are results from our first couple of objects. In the summer of this year, we observed 4 more galaxies, and this is work in prep, but I'll show you this as well. So these 4 galaxies, which host another, I think 6 or 7 Type 1a supernovae, NGC 5643, NGC 1448, and you see the various regions there, NGC 1559, and NGC 5468. Here are the color magnitude diagrams of these, and here are the recovered Cepheids, again, living in the instability strip. And again, we did the wavefront sensing analysis over the course of the times of these observations. There was one hiccup to the C5 element of JWST that was detected on July 16th, and then it was corrected on July 22nd. And fortunately, we didn't have any observations during that period, but even if we did, it's sort of at the 100th of a magnitude level. So we determined that our data has not been affected by that. Later in August, I understand there were bigger events, so your mileage may vary, and you should take a look at this for any other particular observations. Okay, this is the phase recovery that I talked about previously for NGC 5584. Again, the Cepheids live where they're expected to live in terms of the simulations. And then these are the period luminosity relations from JWST, data points here in red, again, versus HST. And this is now in the hosts of 5 Type 1a supernovae. In the hosts of 5 hosts of 8 Type 1a supernovae. And this now covers a total of 1,000 Cepheids in these galaxies. So the size of the sample now is quite significant. Okay, so what can we now say in terms of comparing to HST? And so what I'm plotting here is this is the measurement of distance to these galaxies from JWST versus HST. And of course, this is the usual white space diagram, so everything looks good there. But then we look at the residuals, JWST versus HST. Now, the black points is our baseline combination of filters. This is basically simply replacing HST's near-infrared filter that had low resolution with JWSTs with high resolution. And so that's really the fair comparison to make in black. In green and red, of course, is probing Cepheids at different wavelengths, forming different reddening-free magnitude systems. But those are also in very good agreement. Now, if there had been some kind of systematic effect like crowding that we had failed to correct for with artificial stars that would have to grow beyond the distance of NGC 4258 where we're calibrating, then it would look like roughly this line here. This is kind of a hypothetical model of a systematic error. And that systematic error, it's designed so that it starts at 0 at 4258 because that's where we calibrate. And then it rises so that at the mean of the Cepheid sample, it attains the value of 5 log 73 over 67.5. What is that? That is the size of an error you'd have to make, about 0.17 magnitudes at the mean of the sample in order to solve the Hubble tension. You can see the data is quite inconsistent with that line. In fact, it's inconsistent at the 8.3 sigma level. So just to put a fine point on this, we have stronger evidence against systematic error than we do of the tension itself. If the tension itself is sort of 5 to 6 sigma, our evidence now based on JWST of a problem with Cepheid measurements is 8.3 sigma, much stronger than that. So I think this sort of removes any possibility of seeing a way to rectify this based on an error in Cepheid measurements. Okay, so I'm going to get towards wrapping up then. So my conclusions, we've been very fortunate with JWST, extremely fortunate. The telescope has worked very, very well, far better than we ever could have expected. The discrepancy has sort of held up for 10 years, and we have yet to find, I would say, a way out of it, certainly not on the measurement side that I've seen. Through a series of other measurements by other techniques, we see there's really no precise late universe measurement that's coming in lower than the early ones. And so it's very robust. Exhaustive studies of systematics, variations, and inconsistencies have not found any. And so we're really left with this. The JWST data is very clear that the issue is not related to an error in measurements coming from local measurements with the Hubble Space Telescope. And so that means this is still a great puzzle, and I think very interesting. Is there something missing in lambda CDM? Is there new physics? This is, of course, a very hot topic, and there's been a lot of talks in the CosmoVerse sessions and that are much better than anything I can offer on this. So I won't try to address those, but would direct you to there and various literature sources. So I will end there with thank you for JWST and all the people who have worked on it. And happy Thanksgiving, and happy to take any questions that you have.
Thank you. Thank you so much for the great talk. Any questions?
You classified baryon acoustic oscillations as early method. Well, this is not really the area close to CMB, right?
Right.
So
it's not. So baryon acoustic oscillations on their own are not an early method, but they also on their own don't measure the Hubble constant. They only measure relative distances. In order to measure the Hubble constant with baryon acoustic oscillations, one needs to have a prior on what the size, the physical size of the sound horizon is. And that prior in most cases that you hear BAO presented is coming from the cosmic microwave background. And so it's only
so it scales to some extent to Planck data.
Correct. So if I'm just saying hypothetically, if there was some unexpected physics in the early universe that was changing the cosmic microwave background in a way that changed the sound horizon, and so Planck was interpreting this, I'll say, wrong in the context of lambda CDM, that would imprint all the way to any use of baryon acoustic oscillations to measure the Hubble constant. The alternative is to build a distance ladder locally, calibrate supernovae, and then calibrate baryon acoustic oscillations using supernovae at similar redshifts. And that's been done, in which case you get a high Hubble constant and you get a very different sound horizon. George has a comment or a question.
Since everybody's very shy. But...
And George,
yes.
Nobody has ever called you shy.
Okay. So I've I've played with the data, and there's one thing that really I think bothers me. I mean, I don't object to anything that you've said about, relative distance moduli and the comparison with HST, et cetera, et cetera. But I think that the JWST period luminosity relation. I mean, if you just plot the data as given, then the chi-squared per degree of freedom is about 2. Okay, and what you've done is you've iteratively removed the 3 sigma outliers. Okay, so
meaning, yeah, there's about I think in the paper we present all the Cepheids, including the rejected ones.
You have the rejected.
There's right. About, I mean, there are, I can't remember, but I think there's a handful that are rejected, and we also gave the results with and without.
Yeah, I'm not objecting that. If you include them, it doesn't change things, and so on. It's the question is,
what are outliers?
It's about the scatter, okay? Because we know that the intrinsic scatter, from the finite width, the instability strip, etc., is small from nearby objects.
Right.
So you wouldn't expect. I mean, the scatter has to be caused by the.
So you're wondering what are the outliers? What causes
them? Presumably the outliers are caused because of the scene reconstructions, and not.
So I think there's a few possible sources of true outliers. One is occasionally, and you see this in simulations too, you'll get what I would call a direct hit. So that, a Cepheid is landing exactly on top of another star, so that with JWST, you can't resolve it. Another source would be a true binary companion, where, the other star is also a Cepheid variable or a highly evolved supergiant. So then they are actually unresolvable from each other. And so this is seen in nearby galaxies in the Milky Way. You will occasionally get a star to jump way off it. And when you look at the radial velocity, you can separate the stars and see that there's another star there. So another could be still a misidentification, again, some, not a Cepheid variable, or, even a Cepheid variable that is turned off, so they do cross the instability strip in a finite amount of time. And, it's been decades since they were first observed. So, at the level of, 5% or so, I think I've always seen outliers in Cepheid period luminosity relations.
But you don't see them, from the LMC or M31.
You do. Yeah. Let's see. I'll try to see here. I got to go and look back at this one more carefully, but you will see the occasional outliers in these too. Like things like this down here probably have extreme extinction. And so, you'll have like, that was a strange line of sight. It just doesn't get corrected. And also in the LMC, I'm only showing about 70, but I have to go back and remember this paper. In the Milky Way and the LMC, I think they both had about 3 or 4 outliers, which I think would scale for the JWST samples to sort of like 10 or 15, maybe at that level.
Right. Anyway, the existence of outliers, I thought,
right. And, with type 1a supernovae, we see this as well, to be honest with you.
Oh, sure.
A few percent of type 1a supernovae are outliers as well. I mean, classification is really imperfect in some ways. And so, you can occasionally get, what's called a type 2 supernova Cepheid variable, maybe blending with another star to make it appear brighter, but still having variability. I think, as we do more study of probably Milky Way Cepheids, we may have better and better understanding of the outliers. But as I said, and to be clear, the outliers are not pulling the results.
No, they're not pulling the result. I mean,
one way or another. But I appreciate what you're saying.
I agree with that.
Thank you. Xiang Li?
Hello, thank you. Yes, so my question is, I guess, in your opinion, after crowding, what is the next best systematic to scrutinize the JWST?
After crowding, what is the next best? Say again.
Systematic.
What is the next best systematic that we can scrutinize with JWST?
Yeah.
I'm really intrigued by. I think when you have galaxies that are this well observed nearby, and you could start out with an object like NGC 5584, where you could say, look, this galaxy all by itself at its distance is, 3 sigma from Planck, right? You ought to be able to bring to bear many different ways to measure its distance. So we're sort of picking off the low-hanging fruit. So we can do Cepheids, we can do tip of the red giant branch, we can do JAGB, we can do Miras, and then you can go further and further down the color magnitude diagrams. And as I've talked about, I don't think anybody would, although I'd like to see analyses that could find a way to place this galaxy much, much further away. And so I think our ability to check things like that in kind of interdisciplinary, multifaceted, no longer about Cepheid variables, but many, many ways, is going to become another very powerful way to, for these individual cases where we have extremely high signal to noise to test the distance measurements.
All right, thanks.
By the way, I want to say for full disclosure that Sean is a graduate student of mine, and I did not ask him to ask me that question, but it's an interesting one. So thanks, Sean.
Thank you. And there is a question in the chat. I don't know, Miguel, you want to read it? Or we should read it? Oh, I can read it maybe. If the error in the measurements that you mentioned today is ruled out, in your interpretation, where would it be most likely to find this new physics? Early or late? Any guesses?
I don't really have any guesses, but lots of people have guesses. So that isn't to say that I'm just I'm impressed that it's a difficult problem, and that there are ideas, and which ideas look most promising, or at least is a fluctuating result all the time. Maybe a few weeks ago, I would have been higher on early dark energy. I've seen some other things recently of evolving or decaying dark matter that seemed interesting. But these are, this requires rigorously confronting the cosmological data. And so I don't think I think there are a lot of interesting ideas that can do part of it, but I don't think there's yet been an idea that just fits like a glove.
Thank you. Any other questions?
Hey, I am going to mention to George, the more I think about it, I'm going to direct you to a paper that I recently saw that shows the frequency of binary companions to Cepheids, and how those objects fluctuate off the PL relation. It just struck me as I remember that paper now. And I suspect that will explain most of the outlier issue.
Yeah, thanks.
And, there would be every reason to think that the frequency of such things would be similar in galaxies. It's basically the evolution of 2 stars in a binary.
We have Fisher Watkins.
Thank you. Adam, I'm wondering, in that one galaxy you showed that you had the big tension, how does peculiar velocities play into that?
Oh, that's a great question, especially coming from you. That's a perfect question, Richard. The answer is not at all. And the reason is because there are no peculiar velocities. There's no redshifts used in this calculation at all.
Right,
what you're doing essentially is you're measuring the distance to this galaxy with stars in it, Cepheid variables, that's on the left. And then you're predicting what the distance ought to be by starting at the cosmic microwave background, getting your calibration, right? And with the cosmological model, that gives you a calibration of type 1a supernovae in the Hubble flow at all redshifts. And then you extend that calibration to the type 1a supernova that lives in this galaxy. And that tells you what its distance ought to be given that calibration. And so the redshift of this particular galaxy never enters the calculation. It's the comparison essentially of, I'm going to say, our 2 best standard candles, but calibrated one locally from geometry and the other calibrated from the cosmic microwave background in lambda CDM.
Thank you.
You, Richard Anders. Yeah. Hi.
Hi. Thanks. Very nice talk, Adam. Really enjoyed it. I just wanted to support you on the question from George Eustathiou, who had asked about the nature of the outliers. We have some work in preparation on M101, the closest supernova host galaxy, where we're using UV observations to identify Cepheids that occur in clusters. And what we see is that the majority of the Cepheids that had been rejected as being too blue really are located in locations where you have significant UV flux, which means that there are clusters. And so the occurrence of Cepheids in young star clusters changes their light curves in a way that leads to a rejection based on these objective criteria like color. And that is actually the dominant source of stars in M101 that were rejected. So we understand the physical mechanism by which
So
this,
I think
occurs.
Richard, what you're describing is something pretty similar, which is that when a Cepheid lives, instead of, I was suggesting a binary with, a massive star there, and that happens as well. But if it still lives in the original open cluster that it was born in, and just to say, and Richard's done a lot of work on this, open clusters tend to dissipate in about 10 million years, whereas Cepheids are more like 50 to 100 million years. So there's only a small fraction that are still there. But if they're still there and they're directly coincident with the core of it, and you get that direct blend, then that could produce an outlier. But it's largely rejected by either color selection or amplitude, I imagine, selection, because that's going to compress the amplitude.
Yeah, that's right.
Yeah. Okay. Richard knows more about Cepheids than I do.
Julia has a question.
Maybe I lost this information, but I didn't understand your point of view on the Gaia parallax 0-point offset, your conclusion.
So that was I never talked about that because that is is sort of the precursor of this talk. But the Gaia parallaxes are used as one of three independent anchors here. And so the Large Magellanic Cloud at NGC 4258 are two of the anchors. Gaia parallaxes are the third one. In terms of the Gaia parallax offset, when we analyze the Gaia parallaxes, we leave the Gaia parallax offset as a free parameter in the analysis, and one can solve for it, essentially break the degeneracy between what would be the Hubble constant and the parallax offset, because one of those terms is additive to parallaxes. The other is multiplicative to parallaxes. And so if you have Cepheids over a broad range of parallaxes, then you break the degeneracy between these two, which is to say that you're essentially minimizing the chi-square of the period luminosity relationship in the Milky Way, and that there's a unique combination of the parallax offset and the distance scale that does that.
Thank you so much. Okay.
Thank you. And
Thank you.
happy Thanksgiving, or if you're not in the US, have a turkey sandwich today and think of us.
Thank you. Bye.
Thank you very much. Bye. Bye.
Bye.
Bye.